looking at. One thing that, as far as this building is that we're actually one phase of a phase two building, okay? The original plans were in design that this building was going to be built. Again, it was 10, 11 years ago is when we took occupancy, but there were plans that within the first 5 years, this building would get a duplicate mirror image going up the hill. So they would have gotten rid of ROTC, which is the next building, and the building after that is Enzyme. So basically this would be a mirror image going up the hill. It would have the lab space on the north side, would have the offices on the south side. We'd actually double space as far as lab and double space as far as offices go. What happened was that the funding didn't come through. They wanted to do it within the first 5 years so they wouldn't have to make new contracts, but that was unfortunately not the case, and so it's still in the master plan on the university, but until somebody writes a awfully big check, it's not going to happen for a while, I guess. But the important part of that is that when this building was built, the utilities were designed for its expansion. So we'll see it a little bit in here, and then we can finally go up to the penthouse. The ductwork, the pipes for the heating water, chilled water pipes, the steam pipes, everything is ended at this end of the building, so that when the expansion does come, all they do is connect onto that and continue up the hill. So we're talking about the chill beams as far as being an energy saver for this building. If we take, for instance, an example of like Engineering Hall across the street, I use that one because it's a very, very large spread out building. And so what happens there is that in the winter time, you've got 30-degree air outside. It comes into the air handling equipment. It's warmed up to about 65 degrees, okay? And the reason it's warmed up to 65 is because it's got to travel through large ductwork throughout this entire building and still have some temperature when it gets to the final end. So this air that comes in, it's warmed up to about 65 degrees and then distributed throughout the building. Now, above each office or each space, there's what's called a reheat coil. And basically, it's just a coil up in the ductwork, hot water runs through it, and so you want your office at 68, you want 70, you want 72. So as this air comes down the line through the ductwork, it gets to your office, and then it warms it up those last few degrees to make it comfortable for your particular office. The downside is that in the summertime, you've got 80-degree temperatures outside. That 80-degree air comes in. The air handling units then cool it down to about 55 degrees. Again, what happens is you've got to get some of the humidity out of the air, but also you have to have enough cooling capacity to get down to the other end of the building. And so this cold 55-degree air comes through the building, and then when it gets to your offices, again, it's way too cold for you. So again, these reheat coils actually heat it back up to your 68, 70, or 72 degrees, which is kind of an energy thing where you've got 80-degree air outside, you cooled it down to 55, now you're heating it back up to almost to where it was outside. So that's part of the inefficiency. With our building, again, all of our discharge air year-round, doesn't make any difference, is about 58 degrees. So then it's distributed throughout the building, and then rather than reheat at every single office, it's got larger reheat coils built into the system, and it brings it up in areas rather than individual, which is more efficient. And then the chill beam is more efficient to cool than it is to heat. So then when it gets to your office, then it's actually cooled down to a temperature that's comfortable for you. So that's one big difference between our building, the newer version, and the older buildings. So this chill beam is run by what's called the process chilled water loop. You guys are going to go over to Charter Street. Charter Street is where we get the steam, the campus chilled water, and the air to supply to all the buildings on campus. There's actually 3 plants. There's Charter Street, which you'll see. There's Walnut Street, which is over on the west side by the hospital, and then there's also Cogen. Cogen is operated between Madison Gas and Electric and the university. The original Charter Street plant was coal-fired, and so it was really kind of a dirty environment, and so several years ago, probably 10, 12 years ago, they converted to natural gas, okay, which is a much cleaner fuel. And that was one of the original plants. When they built Walnut Street is with the expansion of the west end of campus and with the university hospital, what we're finding is that there wasn't enough capacity in the chilled water system to keep everybody cool in the winter and in the summertime. So they built the Walnut Street. problem was Walnut Street was an electric plant. That's how they produced the energy there. So what would happen is that on a really hot July day, when everybody has their home residential air conditioners on, and then the campus is calling for cooling down here, they would start up Walnut Street. Walnut, instead of being electric, would actually brown out Middleton because of all the power consumption. So again, Madison Gas and Electric, UW, shook hands and said, well, let's build something together. Okay, so that's Cogen. Cogen is just down the street from Walnut Street, and basically that facility is natural gas fired, so that's how they get their steam. Once they get the steam, then the steam is used to heat the buildings. The steam runs the compressors that makes the central chilled water, and it also makes electricity. So that's where they get the three uses out of the steam, which makes it more efficient. And that way, we've got the extra power to serve the growing campus. We've got the chilled water, we've got the steam, and we don't cause any other issues to the surrounding community. So again, everything's going to come into my building here. There's miles and miles of tunnels underneath campus. Last I think I heard is about 1.5 million gallons of central chilled water. Central chilled water is kept at about 40, 45 degrees. Again, it's got to be at that temperature to get throughout all of the campus and still have some capacity at the end. The problem is that if we ran that 45-degree water through the chilled beams that are up in the ceilings, what would happen is if there was a little bit of humidity left in the air, it would actually condense and start to rain. So it would actually rain from the ceiling in these offices space. So we have to run our processed chilled water at about 65 degrees. So it's a little bit warmer, but still it's got the capacity that we need. There's exchangers in here that do that. It takes the water that's 45 and makes it 65. It's not heated up, it's just the amount of cooling that we put towards it. There's also pumps in here for the heating water. Again, as mentioned, we do have a reheat system here. And again, the steam comes in at 175 psi from campus. And then we've got pressure reducing stations that take it down to 10 pounds for operating our equipment, 85 pounds for operating the autoclaves, glass washers in the labs. And then the 10-pound steam is what operates our air handling units for heating the water and heating the air. So you can go in there if you want to just kind of head down through the side there. Careful, don't touch anything, there's hot pipes in there. Okay, so one of the advantages of this building, again, being a newer building, is the redundancy that's built in. A lot of the older buildings on campus, they would have one circulating pump, so if it failed or would need to be taken out for service, then everything would have to be shut down. So again, with our heating water here, this is our reheat water. These two pumps, one is always running, one is always in reserve, and what happens is that every month they automatically switch so that one doesn't get more wear than the other. Okay, so that's for the heating water. Now, we're talking about Engineering Hall and their reheat system. Again, because of the efficiency of this building, a building like Engineering Hall, the reheat water is at about 180 degrees. Again, because it's got to do a larger capacity, it's got further to travel. Our building here being more efficient, we can run it at 120. So again, there's your energy savings with that. This is where the steam comes in. This is the 10-pound steam. So coming from the tunnel that's behind you, the pressure comes in at 175, broken down to 10 pounds for the air handling equipment and for the converters, and then 85 for the glass washers and autoclaves. And then the central chilled water comes in at the same spot, comes across. We do have two central chilled water pumps here. The central chilled water is for cooling. It's got to go all the way to the penthouse, which is up on the 6th floor. Campus has got some very large pumps that you'll see that actually keep this moving. The problem is that we have a capacity issue. If there's a leak in the system or a failure, our pump will automatically turn on to keep the system moving so that we get chilled water all the way up to the top of our penthouse. There's buildings on campus that are taller than mine. And again, if the system is overloaded on a hot July or August day, their pumps will actually turn back on so that they get the head pressure to get to the top of the building. This is the process chill water pump that I was telling you about for the chill beam. It runs at about 60-65 degrees. The other thing that the process chill water does is it works our environmental growth chambers. It cools some of the other equipment. It cools our IT equipment. So there's multiple uses for that, but its primary use is for the chilled beam. Again, 2 pumps, lead lag, so that there's always one that's in reserve, one is always running. The other thing is that all of the motors in our building, whether they're for pumps or for moving air, they're all variable frequency drives. That's where you get your energy savings from. All of these pumps, 60 hertz is full speed. Most of the equipment in this building runs at 33 hertz, which is just about a little over half speed. And so that's where your energy savings comes from. Questions? Buddy? Okay, we'll go out this way and then go over to the freight elevator.